Okay, in this slide we will talk about the numerical solutions of system of equations, in which we will have several agenda, including the introductions for linear system of equations, and then several approach for numerical solution of linear systems. This will include methods such as Gauss eliminations and as well as LU factorizations. And then for each of the methods, I will not discuss in detail. However, I will show you some Matlab codes that being discussed in the books. Okay, first of all, when we talk about linear system of equations, normally it is represented in algebraic equations in which there is several n unknowns variables such as x1, x2, x3 until xn, and then we will have constants which can be represented in notations A11. It means like for example this one, A11 will be represent the coefficients associated with the first equations and then the first variables, which is x1, and then after that we have A22. A12 means that the first variable, first equations are related to the second variables for that which is x2, so x1 A12. And also we also have known constants here, known constants b1, b2 until bn, which represents the right hand side of each equations. And then this can represent it in the expressed in a matrix form. Let's say, for example, if we take out each a coefficients, we will have matrix A here, which is an n by n matrix. And if we take out the variables only, we have X matrix, which is n by 1, so n rows and then 1 column. The same way as well in the P coefficients, we will have n by 1 matrix that consists the value of the right hand side. Okay, so this can be represented in the this matrix can be written simply by some things like this, and A multiplied by X equals B. Okay, and it is often also represented in the augmented matrix form of the equations, which we will use this one also for this form later on for in the methods like Gauss elimination methods. So here's this form. We have the A part here. The X will represent this one, A part here, and then the B part here, and then each column represent x1, x2 until xn. Okay, that is the augmented matrix equations. Next, okay, there are several methods in which we can use to solve system of linear equations, and basically it is divided into two categories, which called the direct methods as well as indirect methods. Direct methods computes the solutions by performing some predetermined equations. Okay. Predetermined operations, sorry. So direct method here, there are several predetermined operations. So and these methods transform the original systems into an equivalent systems in which the coefficient matrix is normally either upper triangulars or lower triangulars or diagonal, making it much easier to solve. So basically, later on, these two methods were we known as Gauss elimination method and LU factorizations. So the principle of these methods basically was like uh, we are trying to transform the 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 um, the form that we see earlier, the augmented matrix form, into something looks uh, easier to solve the the linear system, such as let's say the coefficients, the A matrix for example in the previous slides, were transformed into either upper triangular or lower triangular or diagonal matrix. The same principle for LU factorizations by transforming into those triangular matrix. LU factorization have two, Doolittle's methods and Cholesky methods. I think we will only study one for these slides. Later on we will see if we need to study the other one. We will only discuss about the Doolittle's methods. For the indirect method, it used some iterations to find an approximate solution. So this one. Normally this one will be ideals for larger systems in which you have more variables and more uh, more equations. Okay, so they are consist of Jacobi method and Gauss-Seidel methods. I don't think we will discuss this in these slides. Okay, the first one we will talk about Gauss eliminations methods. Gauss elimination method is a method for solving the linear equations by reducing the systems into triangular form. So if you remember the augmented matrix earlier, which consists of an A, the A matrix part here, and then the other one is the B matrix parts, and then each of these will represent the variables x1 until xn. So this one we have in this Gauss eliminations we are trying to reduce the A part here into triangular matrix form, so that later on when you substitute from the A part, if it is have the upper triangular forms, it means that all the value here below the diagonals will be 0, right? Well, here this is, let's say this is the diagonals, and then if you have if you're able to transform this into upper triangulars, so all of this will be 0, and then based on this you can easily substitute the value of the last one xn into, it will be equals to b, and finally you substitute it to the upper equations, and finally you will get all those variables of x from 1 until n. And then Well, in order to uh, make the preserve the nature of those linear systems, we cannot uh, we should have some rules to transform those A matrix into uh, its triangular forms. Well, in order to do that, we can only use these transformations using a procedure called the elementary row operations. Well, elementary row operations consist of um, three operations. We abbreviated here into ERO1, ERO2, and ERO3. Okay. What is ERO1? So basically ERO1, you will multiply a row in the augmented matrix by a non-zero constant. So let's say you have like previously we have a matrix A here, and then this is the B part here. So you will multiply the row. So we have, let's say here, row 1, row 2, row 3 until row n. Okay, you are allowed to multiply the value in row 1, 2, or 3. You can select when you it depends on your needs. Let's say here the value is A11, A12 until A1n. Okay, you need to multiply the entire row here with a non-zero constant, a value that is non-zero. Okay, there is one elementary rows. Another one is that we call it ERO2, in which you can interchange the any two rows in the augmented matrix. For example, oh, I want to interchange the this one 3, 3, 1, A 3, 2, and then A 3, n. You want to interchange between the first row to the third row, right? That is possible without changing the nature of the augmented matrix. And then the last one is, I believe one of the most important one is that after you do the ERO1, in which you multiply any row augmented matrix with the constants. Okay, here this one is the ERO1, right? ERO1. You can add the result to other row and then replace those row with that outcomes. Okay. Meanwhile, the row that you multiplied with those constants, the I row, that it will be called the pivot row. For example, let's say here, okay, you want to multiply the row 1 with some value. Okay, row 1 here, so you multiplied it with let's say by 2. Okay, 2 multiplied by row 1, and then you plus this one, this result, to the R3. Okay, and then later on you will replace this value, the R3 value here, by R3 will be equals to the value of the previous R3 plus 2 multiplied by the 2 multiplied by R1. Okay, this is what we have in the ERO3. Okay, to make it easier, maybe we can see the example of these 3 row equations. Okay, let's see the example here. Of course, from the first step will be, in order to operate the Gauss elimination methods, you need to able to transform this system of linear equations into their augmented matrix. So in order to do that, we have the two part. The first one will be here. You need to take all the value of the A, the coefficients in the left hand side, which we call the A matrix, into the augmented matrix versions of it here. So here we have this is the A part here, A multiplied by the X value, and then here will be the B, and then here we have the A part, here B part, and here is the each column represent the x1 until x1, x2, x3, and then xn, right? I believe that it's not difficult to do. It's just to take each of the index coefficient here. This one will be -1 for the A11, 2, right, and then 3 here, 2, and then 3, and then 1, 2, 3, 1, and then the last one will be 3. Okay, check with another sampling. Let's say here, what is this? -2, this will be here. Okay, this should be easy. And then next, okay, now in order to make it a upper triangular matrix, what we need to do is actually, this is the diagonals, right? We want to make sure all the value below these diagonals, let's say this one will become 0, this one also becomes 0, and then this as well as becomes 0, and then this becomes 0, 0, and 0. How do we make that, right? So in order to make those value become 0, we can only use 3 elementary row operations that we studied earlier, right? So those 3 elementary operations is to make sure the operations were not the transformation from those operations will keep the linear systems not changing. So actually you are still working on the same linear equation systems. Okay, so let's check here. First, because we see that the value here of the 1, 1, and then the value of the matrix here in the 1, 1 is -1, and we can use this as a pivot row to eliminate the entries below that one. So here, for example, we want to eliminate the value this one. Okay, make it all below this become 0. How do we do that? So first of all, we can use the elementary row operations number 3 by using this pivot row. Okay, I think I highlighted already. This will be the pivot row. Okay, and then elementary row operation 3, we can multiply the pivot row, okay, with some value, and then plus that with another value with the in the other row. For example, to eliminate this one, the value of this becomes 0. Okay, we can use the pivot row here multiplied by 2 and then plus the second row. So I will write it here. The value of this row wait, yeah, so maybe I'll make another row here. Okay, the value of the row 2 here row 2 will be equals to row 1 2 multiplied by row 1 plus the previous value of row 2. Okay, first let's put the value of row 1 first. So it will be this one minus 1, and then we have 2, and then we have 3. Maybe I use a larger size. Oh no, too large. The previous one is fine. Minus 1, and then 2, and then 3, then 1, and then 3. Okay, and the second row will be the result of minus 1, the row 1, which is minus 1 multiplied by 2, which minus 2, minus 2 plus 2 here. We are successfully get rid of the first row, the second row here. The original value is 2 becomes 0. This is successful. And then 2 multiplied by 2, and it will equals to plus minus 4, it's equal to 0, right? And then 3 multiplied by 2, and then plus 1 here. So 6 plus 1 is 7. And then next 2 multiplied by 1 plus 2 is equals to 4. And then 3 multiplied by 2 plus minus 1 is equals to 5. Okay, so that will be the operation for the second row. What about the third row? Okay, row 3, the next row here, row 3 will be equals to what is the purpose on operating on row 3? Here we want to eliminate this to become 0. So in order to do that, we have here the row 1, the pivot row, multiplied by minus 3, right? Previously we multiplied by 2, now we multiplied by minus 3. Okay, minus 3. So what we have here is will become, the row 3 will become minus 3 multiplied by row 1 plus row 3. Okay, so the value is going to be here's minus 1 multiplied by minus 3 is 3, plus minus 3 is equal to 0, and then 2 multiplied by minus 3 is minus 6 plus 8 come 2, and then 3 multiplied by minus 3 plus 4 is minus 9 plus 4 is minus 5, and then 1 multiplied by minus 3 plus minus 1 is minus 3 plus minus 4 equal minus 3 plus minus 1 minus 4. 3 multiplied by minus 3 minus 9 plus 6 is minus 3. Okay, then we are successfully eliminate this. Minus 3 becomes 0. Next, what we are going to do is this one. Eliminate this one, becomes 0. Okay, so what we have here was like, okay, the pivot row we will multiply it by 1, because 1 multiplied by minus 1 is equal, and then you plus here, it will become 0, right? So the formula for row 4 is equals to 1 multiplied by row 1 plus row 4. Okay, so it's basically just row 1 plus row 4. So minus 1 plus 1 is 0, 2 plus 4 is 6, 3 plus 7 is 10, and then 3 plus 7, yeah, 1 plus minus 2 is minus 1, and then 3 plus minus 4 is minus 1. So basically this will the value, the value of your new augmented matrix. This one here. Still have the A part here, the A part, and then here is the B part here. Well, basically this doesn't change the linear equation system. So you're just making it a new forms of it. Okay, next, after you have this one, what you need to do is that, okay, yeah, actually you want the diagonal here will not be 0. So in order to do that, you can use the ERO2 to interchange these two rows, row 3 with row 2. So after that you will get this new value, yeah, after interchanging those two rows. Okay, so now this one, the new row 2, you can check this. Okay, you want this to become the pivot row because you are going to get rid of everything below here. Okay, everything, this one, make it become 0. As you can see that the value of in the second and in the third row was already 0, so you don't need to operate on that anymore. However, for the last one here, okay, this one, we got it not yet 0. So in order to get rid of that, you can check that. Okay, I think we can create a new row here. Okay, we are just like want to this one, the row 2, your pivot row here, right? And then you want row 3, you don't need to do any operations. However, for row 4 it will be equals to, in order to get rid of the value here, this one, you need to multiply this row 2 by minus 3, right? Minus 3 multiplied by row 2 plus the previous value of row 4. Okay, so your row 4 will become, this one keeps 0, and then 2 multiplied by minus 3 plus 6 is 0, and minus 5 multiplied by minus 3 is 15, plus 10 will be 25, and then minus 4 multiplied by minus 3 is 12, minus 1 is 11, minus 3 multiplied by minus 3 is 9, plus minus 1 is 8. So you can see that the new value of the row 4 will be this one, 0, 0, 5, 0, 0, 25, 11, 8 here. Okay, now move on. We are already able to get rid of this, so we have a new task now. Okay, now it's already 0. Now here this one has not been 0 yet, so this will be the pivot row. Okay. The pivot row now, okay, to get rid of this, so you need to multiply it by minus 25 per 7. Okay, you do these operations and then you will get so 7 multiplied by minus 25 per 7 plus 25 will be, this one will become 0, and then this one 4 multiplied by 25 per 7 plus 11. So you can see the value here. Okay, it will be like this. Okay, finally you get the final form, look like this. This is the value of A matrix, and then here will be the value of B. How do you return these solutions, the new augmented matrix, into the original form to get the value of X variables? Okay, now we move on to the substituting it back here. So basically here's, let's try to remember this. Okay, each of these represent the value of this one x1, this one x2, this one x3, x4, right? From the last row, row 4 here, it means that 0 multiplied by x1, 0 multiplied by x2, 0 multiplied by x3, and then finally x4 multiplied by minus 23 per 7 were equal to minus 69 per 7 so based on this you can solve the linear equation. Okay, here means that if you move all the coefficients and then left the x4 on the left hand side, you will get the x4 will equals to 3. Okay, after you get this one, the value of x4 by substituting it back to the original value, so x4 will be equals to 3. Okay, now you can move up to the one upper equation here in the equation 3. You have the value of x4 is equals to 3. So now you know that when you these three equations will represent okay, here each of the column x1, x2, x3, and then x4. So it means that 7 multiplied by x3 plus 4 multiplied by x4, right, will equals to 5. And you know that the value of x4 is equals to this one, 3, right? So here you can substitute it back to become 7 multiplied by x3 plus 12 will be equals to 5, right? So then you have 7 multiplied by x3 equals to 5 minus 12. Okay, so 7 multiplied by x3 will be equals to minus 7, then x3 will be equals to sorry, wait, this is wrong. Yeah, this is correct, -1, right? So here's, or the other way we can calculate it here. Put all the x3 on the left. X3 will be equals 1 divided by 7, 5 minus x4. So you can get the same way. Minus 7 per 7 is equals to -1. Okay, now you get the x3 is equals to -1. Then you do that one to the next equation here. Okay, so basically this one, they move it to the right hand side, everything's okay. So it will be like -3 plus 5x3 plus 5x3 plus 4x4 minus 3 will divided by 2 will equals to x2. Okay, here's, so you put all the value that you can found earlier. So it was like x4 is 3, x3 is -1, and then you try to sum it, you just try, and then finally it should be x2 equals to 2. And the final equations is that top, the row 1 here will be minus 2x okay, yeah, multiplied by -1 first, so my 2x2, 3x3, 1x1 minus 3 will be equals to x1 here. Okay, then you put all the value x4, x3, x2, then you will get x1 is equal 1. So finally we are able to solve the linear equations using Gauss eliminations. Then we got the value of all variable x here. Okay, there is another approach that can improve the Gauss eliminations process called partial pivoting. Using this approach, you are able to reduce the number of steps you are using to solve the Gauss eliminations approach. So basically, it's like this. So for each row I of the A matrix, okay, maybe I'll remind you again, we have two parts here. The A part in the left hand side, and then B part here. For each row, so let's say row 1, row 2, row 3, row 4. Okay, you need to find the entry of the largest value. We call it M. Okay, so A have several entry, A11 here, maybe A12, A13 until A14, so like that. You find the largest value of that, you call it MI. So here MI. MI. It's too small here. Maybe I'll just use the word only. MI. What is MI? MI is the largest absolute value. So you absolute, even it's negative value, you absolute it first and then find the largest one. Call it MI for each row. And then at each row, you will find the ratio of the coefficients of the x1. So now here you have x1, okay, and then you have a11 there, and then you want to find the ratio of the the absolute value of the coefficient. So let's say here you have the A11, A row 1, column 1, okay, A column 1, A row 2, column 1, all of this. So this one 2 1, this one A 2 3, sorry 3 1, this one A 4 1, okay, rows and columns. So you find the value of the R, here's formula, absolute value of this A divided by their M, which is the largest entry on that row. This one, they may have their own M here, for example. The value of their M2, let's say here M2, here maybe M3, this one maybe M4 here, okay. So you find the ratio. So each of the row will have their ratio value, R1, R2, R3, R4. Among this R value, okay, what you need to do is that you need to find or pick the largest value of those ratio, okay. It means what? Means that whichever row is responsible for the maximum value will be picked as the pivot row. So you are going to eliminate the x1 to obtain to the new systems. So basically this will help you to reduce the number of the Gauss iterations, okay. So after that you just need to you will able to reduce the operations, okay, to just work. Let's say at the beginning you will reduce the first row and then you will done with working with the first column here, okay. And then in the new iterations you just need to work on the partial systems, okay. Here's only the things that left haven't solved yet, okay. And with the same logics in step 1, 2 and 3 here, you can reduce it into smaller versions again, so that finally you will able to solve it more efficiently, okay. Let's go to the example to make it easier, okay. Let's say this one, we have the linear equations already being represented in its augmented matrix versions. And first, of course, you will need to detect which one is the M value for each row. Right. And then we are going to work on the first column here. So you will find the value of R1 is the value of the A11 minus 4 divided by the value of their M, 5 here. And then 6 here for the row 2, 6 divided by 7. All will in the absolute value. And then the last one, row 3, is 2 divided by 2. Okay, based on this, you can see that which one is the largest value of the R will be this one, right? Row 3. Correct? Yeah. So you pick R3 as our pivot row. Okay. So because you want to move R3 to be the pivot row, so you move this one up. So you swap the R3 here, R3, this one with the other one here, swap it, and then after you use that one as the pivot row, okay, I think it's not really clear here, so let's just rewrite it. So you will use it to, after you swap it, it will become, this one is the value of 2, and then -1, and then 1, and then 6, right? Here we still have 6, 7, -3, and then 2. Sorry, this one is not 6, but yeah, this one's 6, correct. This one become -4, and then -4, -3, and then 5, and then 0. Okay, and then you do the Gauss elimination to get rid of this value to here, 6 and 4. So you can like what we have earlier, so row 3, this one, row 2 will be equals to -3 multiplied by row 1 plus the previous row 2, right? And then here also row 3 will be equals to 2 multiplied by row 1 plus previous row 3. Okay, you do this process like what we have, and then you will got to the value where this one sorry, I will erase this one, and then you will get rid of the value of the below here, so it becomes 0. Okay, it means what? It means that later on you just need to work on this part, okay, this part, and then you get the value of, you identified again which one is the M here, this one is the M here, and then for this one is the M here. So means that the ratio you calculated 10 divided by 10, and then here -5 divided by 7. You know that, okay, the second part will be the row, okay, the pivot row. So you get rid of what? You get rid of this one here, okay. So this will okay, now it's already become a triangular matrix. Then you can substitute it back, and then you will get the value of x3, x2, and then x1. This will save you a lot of iterations. Okay, that will be about partial pivoting. And finally, for the Matlab code, I don't think we are going to explore this in detail right now, but if you want to see that basically this code consists of two parts. First, they will use the Gauss elimination function they create and input the A and B value, okay, and then here's we're using the partial elimination. So you can see that they find the M value first, and then calculate the ratio, okay, and find the maximum one that have those ratio, and then they will use this as the pivot row and then work on the get rid of all the zeros value under those pivot row, and then do those iterations n time for all the matrix. After you get the new value of the augmented matrix AB, you will use a formula, another function we call it back substitutions to get the value of x. And then here is the function of back substitutions, in which they show you that, okay, if we have the augmented matrix, you can back substitute from the last row and then find the value of x. Okay. If I recommend you try the code, but for this these tutorials, I won't explain it in very much detail. Okay, in order to understand the Matlab code, here's are some recommendations. First, of course, you need to, I think, in order to understand the algorithms deeply, you can try to create the pseudocode or flowcharts of working on using Gauss with partial eliminations. And in Matlab, I think we can use the debugging functions by try to go step by steps into each line of the codes. Well, I think that's all for now about the Gauss elimination method. Next, we will discuss about the LU factorizations method.